Yeah, guys, beautiful evening. Uh, yeah, I can see you guys there. Good evening to everyone. Good evening. Good evening. Marvelous, good evening. Tammy, good evening. Alex, good evening. Foxy, good evening. Oh, Tammy said it's been a long time. Adebola, is Adebola here? Okay. Good evening, Adebola. Guys, good evening. Enoch, good evening. How you guys doing? How was your day? Hope you had a great day. By the way, guys, how did you find the test, the quiz test? Good evening, Larry. Good evening. Oh, your day was boring, really? Marvelous. Good evening. How you doing, Elendo? Oh, that's great to hear that your day was great. Good evening, everyone. Good evening. Oh, boring. What is punchline talking about? Where did you see me wearing short sleeve? are you are you seeing a vision there? Good evening, guys. Well, the quiz was very simple. Oh, sorry, my bad. Or probably your home good, right? Was it my bad? I think it's great. It's great that you found it simple anyway. So that means you enjoyed it, right? Oh, Punchline said he's seeing me right now. Okay, that's nice. Okay, interesting. Okay, you're good, all right. That's great to hear. So, it's quite very interesting. It's quite very interesting. So I guess you guys already have a very great introduction. Yeah, somebody's asking how am I? I'm doing really great. Uh, I'm doing really great. Thank you very much for asking. Uh, so you have probability right in front of you, right? So that's really great. It's great to hear that you guys had a great day. Probability. Somebody's asking how tough probability can be. Let me be very frank with you guys. Sincerely, sincerely, probability can be very tough. Let me be very honest, right? I don't want to kid you too much because it has uh, it has lots of detailed question that can be asked. So you have to be very smart. All right, you have to be very very smart. So I don't worry. You would see some questions you would see in your test. I mean your physical test, and if you're not well grounded in this, and that's the reason why I'm trying to break it piece by piece, because uh, I'm very concerned that I don't want to load you guys with, just load you and leave. I want you guys to understand the whole detail on how to tackle questions. Honestly, if I start to bombard you with technical questions right now, you'll be so shocked. It will look like you never learned anything because there are lots of technical questions on that probability. So just you don't have to be scared about nothing. All you have to do is just keep moving and make sure you pay attention to every detail. Like right now I want to get you guys into a very important part of probability, and that's the use of cards. You can do the quiz. The quiz is still up there. I've not removed it, and so it's still up there. You can do the quiz quickly. So I want to get you guys into cards because I understand that not every one of us are very used to playing cards. So I want you guys to be very familiar with that so that when the time comes and you're being taxed with questions on cards, you don't, you can't talk about an experiment you don't know about. Like, just take for instance, you don't know about a die. You don't know how a die is. Imagine you don't know that a die has one, two, three, four, five, six. And they tell you to answer a question around a die. I'm sure you know that it will be very hard to answer such question. That's the reason why it's very vital you understand every sort of experiment that is very much common under probability. So guys, let's get right into it because I think we have a lot to cover. So uh, pick your notes, pick your pen, and let's move right into it. Uh, when you have a pack of playing cards, I'm sure you all recollect what we did yesterday. We talked about some important uh, concepts around probability. The first of which was the word sample space. Don't forget, we define sample space as a set of all possible outcomes. So that means for you to be able to solve questions regarding cards, playing cards, you have to be very aware of what are the total set of possible outcomes. So guys, let's get right into it. When you have cards, I want you to know these simple details around cards. Number one, the total number of cards you have is 52. So a standard deck of cards has, the first one is we have 52 cards in total. That's the first thing you must note. So that means the sample space, whenever you are dealing with a standard deck of cards, is 52 because the total cards you have is 52. Now, these 52 cards are splitted into four suits. So we have four suits, and I'm sure you know some of them. I'm sure you know them if you are very much familiar with it. We have hearts, we have diamond, we have clubs, and we have spades. All right. Uh, just to be a bit more like having, I want to use the color of the cards to indicate them so that at least you can relate to them as much as possible. So you can see the colors I used there. That's actually the color you would be seeing. Uh, the third one is clubs. All right. The club looks like this, more like something of this sort.
it may not be a very perfect diagram, but something like almost like a flower or something. And then you have the spades looking. I think I told you guys already I'm a very poor artist. I don't know when I lost my talent for drawing, but how hard it is to draw a spade. So it's something of this form. So if you can go online to just check for all these things, you would see the real pictures. So these are just who is Marvelous? What was Marvelous saying? So all right, okay. So generally we have these different four suits when you're dealing with cards. No, you somebody is asking about using what? This is different from this is not the standard deck of cards we're talking about, not the what. And majorly when you are asked questions around cards, I want you to understand that this is what you're talking about. This kind of cards is what you're talking about. Now, I want you to understand that in all these suits uh, you have 13 cards each. So you can do the math already. That means for arts, you have 13 cards. For diamond, you have 13 cards. For clubs, you have 13 cards. And then for spade, you have 13 cards. So obviously, if you go on to add this whole 13 in four places, you'll be getting obviously 52 cards. Now, you also need to understand that these 13 cards, they also have subdivisions also. So each of these 13 cards, look at their constituents. We have A, which is obviously what we call ace. Then we have the number 2 to 10. Then we have J, which is for jack. Then we have Q, which is for queen. And then you have K, which is for king. All right. So we have all this. This is the different divisions for it. That means when you're dealing with a suit hat, you have 13 cards, right? If you go on to make these calculations, you will see 2 to 10. Obviously, that's 9 different cards there. That's 9 cards. Number 2, number 3, number 4, number 5, number 6, up to number 10. Then you have A, then you have J, you have Q, then you have K. If you do the sum, you will see that this will be a total of 13 cards. So each of the suits has this constituent. Now, this is very vital because, as you probably have seen in some of the questions you have solved earlier, you could be asked to get probability of, for instance, what's the probability of picking a jack? What's the probability of picking a 2? So if you do not know the event space, you cannot define the event space, I'm sure you know that will be very hard for you to solve. That's the reason why you have to take note of all these things so that in some moment now we'll be solving questions around uh, cards. So I want you to be able to really answer them. Now I want you to also know that we can also classify the cards based on color. It's a very common question also. For instance, you can be asked to uh, talk about what's the probability of you picking a red card and what's the probability of you picking a black card. Now, so following that, you obviously know that by color, we can classify cards based on red cards and also black cards. All right. Now, I'm sure you know uh, how many cards will be red, obviously, because I told you that you can see the color I used here. Hearts are color red, diamonds are color red also, clubs are color black, spades are also color black. So this means obviously we have 26 cards that are red and 26 cards that are black. Of course, these 26 cards that are red constitute both the heart and the diamond. All right, good. So these are some of the, I'm sure everyone right here understands the importance of all this detail, because if you do not know all this detail, you would find it difficult to answer any question regarding cards. All right, good. Now, we can also classify cards based on number. That means number cards, the cards that has number. And obviously, you know that we have 2 to 10 for each of the suits, right? And for the face cards, we have J, Q, and K. All these are face cards, J, Q, and K. And then we have aces. Ace is a very important card. So there's a common saying that it says is the ace you keep off your sleeve. Ace is quite very important, and we have just 4 of those. So we have 4 aces, and then we have 4 jacks, 4 queen, and 4 kings. Now we have obviously going to be 4 twos and 4 of all each of the numbers. So all those details are very vital, so that when you get into, like, let me just give you some random questions. Can anybody in the chat, or everyone, can you give me an answer to this question? Can you give from all I've just said? From all I've just said now, can you tell me the event space for drawing a heart? Give me the event space of drawing a heart. Give me the event space of drawing a heart. What's going to be the event space of drawing a heart? Oh yeah, give me. The answer is right in front of us, but I just want to, I didn't ask you to solve any probability. I just told you to do the event space of drawing a heart. A heart. A heart. Yeah, the event space is what I asked for. You guys should not confuse event space for number of elements in the event space. Event space is a set, guys. Event space is a set. Yeah, the unnamed guy, whoever that person is the only person that has gotten the event space. Everybody writing 13 is not, that's the number of elements in the event space. The event space is actually the elements inside that event. So drawing a heart, obviously we have 13 different cards, and we have A, 2 to 10, J, Q, and K. All right. So can you give me what's the event space of drawing a red card? What's the event space of drawing a red card? Can you give me that quickly? The event space of drawing a red card. The event space. Some of you are still making the same mistake. I did not say the number of elements in the event space. You can find a way to always shorten your answers. But event space, I want you guys to understand how to bring out event spaces. Thank you. Emperor has gotten it. Heart and diamond. Heart and diamond is actually the correct answer. Heart and diamond, Alex to got that. Heart and diamond, because those are the two. So, and the number of elements in the event space now will be what? 26. Now, guys, can I get the event space for drawing a king? The event space of drawing a king. The event space of drawing a king. The event space of drawing a king. What's it going to be? What's the event space of drawing a king? Okay. At diamond, club, spade. Good. Okay, I can see you guys. Yeah, good. No, it cannot be one element, guy. That a modular, it cannot be one element. Exactly. Thank you very much. I like that you guys are participating. King, yes. Olatunde Marvelous is also on point. So obviously the event space of drawing a king, because for each of these suits, you have a king each. You have a king for hearts, you have a king for diamond, you have a king for clubs, you have a king for spade. So that's the event space we actually feature that of heart, that of diamond, that of club, and that of spade. That's really great. So I believe at this point now, you guys should be ready for any sort of question. I believe that's just all I want to say about this card. Now it's time for you guys to answer lots and lots of questions. All right? Great. So you guys should stay in the chat box, because at this point, I'll be throwing questions to you on everything. Now we are, I've been dealing with event spaces, sample spaces. Now it's time to solve probability, favorable or another way of seeing that probability of an event, let's say event A, will be n of that event over n of s. All right. So we have the number of elements of that event space. And that's why I'm particular about you being able to bring out event spaces. So what is the number of elements? You go and fish that out. Then what's the number of elements in the sample space? You go and fish that out. Guys, let me quickly ask this question quickly. What is the total number of possible outcomes when dealing with playing cards? What is NS? What is NS? What is NS, guys? What is NS? What's going to be NS? Okay, good, good, good. Yeah, that's exactly what I want to hear. So you understand the sample space. Of course, the sample space will constitute, in terms of the sample space, if I just ask you what is the sample space, the sample space will constitute of all the cards at diamond, clubs, and spade. That's the sample space. But the number of elements in that sample space will obviously be 52. Yeah, that's very nice. So guys, grab your pen, grab your paper. It's time for you to solve questions. So we are solving probability now. We're not interested in event spaces now or sample spaces. We are interested in the answer. So, and just go on to use this formula, the number of elements in the event space over the number of elements in the sample space. You will never go wrong. So guys, it's time for us to kick off. Question number one: 3 coins are tossed. 3 coins are tossed. 3 coins are tossed. 3 coins are tossed. All right, 3 coins are tossed. Write the sample space. Do that very quickly. If you have that, you don't have to do it again. If you know how to do that, if you have that somewhere in your notes, but if you are joining us for the first time today, you can go on to write that. So 3 coins are tossed. 3 coins are tossed. So write the sample space. All right. Now, question number one under that, or probably question number two: what is the probability of getting exactly 2 heads? Probability of getting exactly 2 heads. So that's the first question. Guys, have you written the sample space? Are you people having issues with the cards? Am I getting? Are we having? We're done with the card. Probably when this video drops, you can go back to relate with the cards. All right. Now, this is the first question. 3 coins are tossed. You're told to write the sample space. So, guys, what's the first answer? The sample space, can you people just give me quickly? I know you guys know it, but can you give it? So we have the sample space being what? HHH. We are not going into explaining this because we did that yesterday. You can check out the video yesterday. HTH, HTT, THH, THT. How many is this? 1, 2, 3, 4, 5, 6. What's the next one? What's the next one, guys? TTH. And then we have TTT. Good. Now, the question said, what's probability of getting exactly 2x? So the question there is obviously asking you, probability of that event will be what? N of that event over ns. So for starters, what is ns? N number of elements in this sample space is 1, 2, 3, 4, 5, 6, 7, 8. And I taught you the way of getting that without having to even list it all out. Of course, that will be 2 raised to the power of the number of coin. Here we're dealing with 3 coins, so that'll be 2 raised to the power 8. Sorry, 2 raised to the power 3, that'll be 8. So that means whatever is going on here will be over 8. So the next question said, probability of getting exactly 2 heads. The event space of exactly 2 heads will actually be what? The event space of exactly 2 heads. So you have to go into this box now and check out where you have exactly 2 heads. This is one of them. This is one of them. This is one of them. I can see just 3 of them. If I'm asked to write the sample space, sorry, the event space, that will be HHT, HTH, and THH. This is the event space for that. All right, this is the event space. So the number of elements in this event space is obviously what? 3. So the probability of that event happening will be NE over NS, which is 3 over 8. That's how you solve questions on probability. And you cannot go wrong. I can assure you, all you have to do is just follow these steps I'm giving you. You can never go wrong. Question number 2. Question number 2. I'm sure everybody understood that. All right. Question number 2. What is the probability of getting at most 1 tail? The probability of getting at most 1 tail. So we're done with this. We want to do the next one. Probability of getting at most 1 tail. So just follow the same procedure. That's all that will give you your answer. You don't have to sweat it at all. It's very simple and straightforward. Follow the same procedure. Make sure you bring out the event space. Of course, I already brought out the sample space. Bring out the event space and go on to find the number of elements in the event space and then put that all over the sample, the number of elements in the sample space. Do we have answers? Okay, people are saying 4 over 8, 1 over 2. All right. So let's see it together. So the very first thing you have to talk about is that event. All right. So the event of having at most 1 tail. Let me get this off. Because this is another event we're dealing with. So at most 1 tail. Okay, 3 over 8. Okay, we'll see. Let's see it together. Now, at most 1 tail means the highest you must see is 1 tail. right? The highest you must see is one tail. So anything that has anything more than one tail is not part of that event. All right. So let's see what the event that event will be. The event space will obviously be, they said at most one tail. The first one we have here has zero tail. This one has one tail. So obviously I know that this is part of it because it said at most one tail. Zero tail is included. We are okay with zero tail and one tail. That's what this event requires. So you must, anyone that has zero tail is included in the event space. Anyone that has one tail is also included. But anything more than one tail cannot be included because it said at most one tail. HHH is part of this event. HHT is also part of it. HTH is also part of it. Because I can only see one tail here. HTT cannot be part of it. THH is also part of it. THT never, because that's two tail. TTH not possible. This is two tail. This is three tail. So this obviously is the event space for at most two tail. And the number of elements of this event space is 4. So your probability will be 4 over, of course, 8. That will be 1 over 2. Great, guys. I can see many of you got the answer right there. That's really great. Yeah, this is real progress. I'm really proud of you guys and your progress in this on this topic. All right, go on now to solve this. Find probability of getting all heads. Okay, somebody is asking how is HHH part. Of course, they said at most, that means the highest must be one tail. HHH is zero tail. Is actually part of it because it still conforms to at most one tail. Zero tail is still under at most one tail. All right. So the next question said the probability of getting all heads. That means the only thing you want to see now is heads. All heads. What's the probability of getting all heads? So we're done with this. We can take this off. Take this off. Now we're solving all heads. All right. So guys, as you can see me do, the first thing you want to do is to go on to identify your event space. That was what we learned yesterday. There was a reason for that. So what's going to be my event space here? The event said probability of getting all heads. Of course, all heads. Check through everywhere. This is the only one that has everything all heads. HHH. We have only one element in this event space. So obviously, N of E will be equals to 1. So the probability here will be 1 over, of course, the sample space, 8. Hope you guys are really enjoying this. Now, find the probability. We're in the next question now. We can move faster now because I can see you guys are really following. Probability of getting at least one head. The next question said at least one head. Probability of getting at least one head. Probability of getting at least one head. Probability of getting at least. Make sure you pay attention to the question properly before you solve. Probability of getting at least one head. At least one head. That means the least thing you must see is one head. You must not see 0 head. One head is the least. Go through your whole sample space. One head is here. This is 3 head. This is 2 head. This is 2 head. This is 1 head. This is 2 head. This is 1 head. This is 1 head. This is 0 head. This is the only one excluded out of this my event space because obviously this one has 0 head, but every other one has 1 head. So I don't, you know, the event space will obviously be HHH, HHT. You can see this is very vital. What I'm doing right here is very vital. Please, you follow this same blueprint so that you don't ever make any mistake. So this is the event space, and the number of elements in that event is 7. So this will obviously be equals to 7/8. This is how you tackle question when you're dealing with probability. All right. Another set of questions now. 4 coins are tossed. Now, no longer 3, 4. 4 coins are tossed. How many outcomes are possible? 4 coins are tossed. How many outcomes are possible? Question said how many? Question said how many? Thank you. I can see the answer. 13 is not correct. 4 coins are tossed. How many outcomes are possible? I told you guys already, the formula we use is 2 when dealing with coin raised to the power of n. N here signifying the number of coins you are tossing. So for this situation where you're having 4 coins, that will be 2 raised to the power of 4, that will be 16. All right, and I already explained to you how you deal with getting all the elements of the sample space. Now, I'm going to give you a moment to practice right now in your notes. Please, can you go on now and bring out all the sample spaces? And then, because I want you to, these are the 2 questions you want to answer. The question number 1 is probability of getting exactly 3 heads. Exactly 3 heads. And question number 2, no head. So we're in a new set of questions now. 4 coins are tossed in this case, not 3. 4 coins are tossed. So, of course, go on to write the sample space and go on to find the probability of getting exactly 3 heads. That's the first question. So please, you need to get yourself used to solving all these kind of questions, because so that you don't go on practicing in the exam hall, right? So have you guys been able to draw out the sample space for 4 coin? Okay. So the first question is actually, the answer is 4/16. If you go on into your sample space and you try to look for the number of events that has exactly 3 heads, the number of times when you had exactly 3 heads, it's 4 different times. We may not go on to write all the sample space now, because it's going to be quite many. We're going to have 16 different experiments or outcomes, possible outcomes rather. And the first one will obviously be HHHH. The last one will be TTTT. And then there will be so many other 14 different outcomes in between them. Now, we don't want to go on to write all this. I taught you how to bring out this yesterday. Of course, if you are new here, the way to bring it out is to go on to use the sample space for 3 coin and penalize that with 1 coin HT, and then bring out all the possible outcomes that comes from there. You can go on to check the video of yesterday to be more perfected in it. Now, for the question I asked, probability of getting exactly 3 heads will actually be 4/16. That means you have 4 outcomes that gave you exactly 3 heads, and the NS is obviously 16. That will obviously give you a 1/4, right? Now, the second question said the probability of getting no head. Next question now said probability of getting no head. That means 0 head, no head, 0 head, no head. Quickly, if you are yet to give us a thumbs up, can you do that very quickly? Give us a very great thumb up before we continue. All right. So exactly 3 head. I told you already that is 4/16. Then 0 head. Of course, I do not need to say so much there. 0 head. That means you don't have head at all in it. I'm sure you guys can see from the way things are going that in all of these cases, you always just have one that will house 0 head, and you have one also that will house 0 tail. So, of course, the number of elements in the event space of 0 head, the event space is actually just going to be TTTT. That means the event space for 0 head will be TTTT. This is the only event this is the only outcome that is 0 head. And then in that case, of course, your sample space still remains 16, and your event space will be 1. Of course, number of element there is 1. So this will be the answer, 1/16. Good. So you are making real progress with this topic. This question, I want you to give me in just 1 second. A coin is tossed five times. What is the sample size? What is the sample size? A coin is tossed 5 times. What is the sample size? Thank you very much. 32. And I'm sure you know how to. All right. That is the sample size. That's the total number of possible outcomes. So, guys, take this question down and solve it also. Let me give you just 30 seconds to solve this. Hopefully, you can do it. Find the probability of getting more heads. Probability of getting more heads than tail in 3 tosses of a coin, obviously. The probability of getting more heads than tail in 3 tosses. To find the probability of getting more heads than tail in 3 tosses of a coin, obviously. You guys are shooting your answers already. Wow, you guys I'm really proud of you guys. I love your energy. I love what you guys are doing. That's really nice. So more heads than tail when you toss 3 coin up. That means of course you remember the sample size the sample you have. More heads than tail. More heads than tail. Of course, if you're going to have more heads for 3 tosses, that means you are okay with seeing 3 heads. You're also okay with seeing 2 heads. Am I right? Because you are looking for more heads than tail. Now, if you go on into your sample space, you would see that the event of seeing 3 heads, of course, you have one of that, and then you also have 2 heads where you have HHT, then you have HTH, then you have THH. These are the 3 outcomes that signifies more heads than tail. You can see here we have more heads than tail. There is no even we don't even have tail at all. So this obviously this is 3 heads 0 tail. This is 2 head 1 tail. This is 2 head 1 tail. This is 2 head 1 tail. You cannot pick anyone that has 2 tail 1 head because that will not be more head than tail. All right. So the number of elements here is obviously 4. And then the probability of this event will be 4/8. That's 1/2. Okay, so that's really great. You guys you're doing really great, and that's so nice. Now, two die are rolled. Two dice are rolled. Two dice are rolled. Write the sample space. You got you guys that probably already did this yesterday, you can just go on to look through without your notes. You don't have to rewrite everything from scratch. I said write the sample space, not giving me the number of elements in sample space. So two dice are rolled. Write the sample space. All right. Write out the sample space. Write it out and make sure you have it. If you have it already, of course, you can use it. But if you don't have it already, please make sure you spend your time quickly now to go bring it out. And if you have it already, just bring it close to you. But if you don't have it already, just go on to have it done. I will not do it from, I will not, of course, complete this. I just want to show those of you that probably you need to see it. How you bring out the sample space for two dice. This is the first dice. This is the second dice. So the sample space for those, the two tosses in short, the toss of two dice will be this: 1-1, 1-2, 1-3, 1-4, 2-1, 3-1. You fill in all these places that way. All these values you have here are the outcomes that can happen when you toss two dice. Now, this is the first question now, all right? The first question is find the probability of a sum of 7. Find the probability of a sum of 7. Find the probability of getting a sum of 7. Find the probability of getting a sum of 7. What is your answer? A sum of 7. So you see the reason why I wanted you to highlight this whole sample space out, because if you don't have the sample space handy, you may not be able to solve this question properly. So if you have brought out the whole sample space, as I said, for you to find a sum of 7, of course, I'm sure you know that this is where it's going to happen. 5-1 will not be part of it, but 5-2 will be hit. 5-2 will be included. 4-3 will also be included as a sum. You can see the sum. 5 plus 2 is 7. 4 plus 3 is 7. 6-1 will be included also. You can see this add up to 7. 3-4 will be included also. You can see this is giving you a total of 7. 2-5 right here. 2-5 will be included also. And we have 1-6. So obviously 1, 2, 3, 4. These are, if you're asked to bring out the event space, of course, bringing out the event space, what you have to do is write E being, of course, 6-1, 5-2, 4-3, 3-4, 2-5, and 1-6. This is the event space for a sum of 7. All right. Now, great. If you are, of course, you can obviously go on to find the number of elements here. This is obviously going to be 6. So for you to find the probability of the sum of 7 happening, that probability of that event will be 6 over the total number of possible outcomes. That's the number of elements of the sample space. Of course, for tossing two dice, the number of elements in sample space is 36. So that will be 6 over 36, and that will give you 1/6. All right. This is how you tackle questions on probability. All right. Go on to solve this next question. Find the probability of a sum of 10. Find the probability of a sum of 10. a sum of 10. Find the probability of a sum of 10. The probability of a sum of 10. Okay, we are having different, okay, 3 over 36. Now, a sum of 10 will obviously need a communication between these values. Sum of 10, of course, I know 6 and 4 will give me sum of 10. And sum of 10, 5 and 5 will give me that also. 4 and 6 will give me that also. Is there any other one I'm seeing here that can give me the sum of 10? Not exactly. So obviously, your event space, you can see how I always do my own work. I tend to bring out the event space first. This is a way of ensuring you don't go wrong at all. So if something is wrong, you can easily trace your answer. All right. So this is the event space, and then your number of elements of your event space is obviously 3. The probability of this event happening will be 3 over the total number of possible outcomes, which is the number of elements in your sample space, 36. That will be 1 over 12. All right. What's the probability that the sum is even? What's the probability that the sum is even? So now when you are done doing the sum, you got an answer that is even. It's an even value. It's an even number. What's the probability that the sum is even? Okay, do we have answers? Someone wrote 1 over 2, someone wrote 1 over 12, someone wrote 1 over 2, 1 over 3. We have different answers. Of course, the key to success in this is obviously you having a very great sample space already written close to you. So if you have that, of course, you can't go wrong. So can you write out the elements of your sample space? Is it very strong? Of course, if we go on, let me go on to just identify this. The sum being even, this is one of it. 1, 1 is one of it. 1, 2 cannot be one of it. 1, 3 is one of it. 1, 4 cannot be one of it. 1, 5 will be one of it because 1 plus 5 is 6. 1, 6 cannot be one of it. Now, 2, 1 cannot be one of it. 2, 2 will be one of it. 2, 3 will not be one of it. 2, 4 will be one of it. So can you tell me now, following the process I just laid down, you go on to write how many different, what was the number of elements of that event space, guys? What was your number of elements? So the number of elements you will have there should give you a total of 18. All right, thank you, 18. So you see that going on to find the probability of the sum being even, that will be 18 over 36. That will be 1 over what? Over 2. I'm sure you guys are gaining greatly from this. All right. What's the probability of getting at least 1 6? The probability of getting at least 1 6. Probability of getting at least 1 6. So this is to expose you to lots of questions, and it will really help you to be able to tackle any sort of question you see. Okay, someone says 7 over 36. Somebody said 11 over 36. Now, probability of getting 1/6. That means you have 1/6. Okay. Okay. Now, look at what you have here. Getting 1/6. Everything here, because this is going to be 1/6. This is going to be 2/6, 3/6, 4/6, 5/6, 6/6. And the question said probability of getting at least 1/6. If you look at the tone of that question, that means this is at least you can just see one of 6 was gotten here, 6 was gotten here, 6 was gotten here. All through, you got double 6 here. All right. Now you had double 6 here. Now, this is also still part of it. All right. In this case, also, you could have 6/1, 6/2, 6/3, 6/4, 6/5. You can see that now you're just supposed to go on to count all these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are all the elements of the event spaces, the event space. If you are told to bring out the event space, this is all what you bring out. At least 1/6. 1/6 happened here, 1/6 happened here, 1/6 happened here, 1/6 happened here. But here we had 2/6. It's still part of it because the question said exactly 1/6. Guys, what's going to be the answer if they said exactly 1/6? If they said what exactly 1/6, that means you got exactly 1/6. The probability of getting exactly 1/6 will be what? 10. Thank you. 10 over 36. Because in that case, your event space will have all of this except this double 6. So this double 6 will be the odd one out because this would have been 2/6. But in this case, since the question said exactly 1/6, sorry, it said at least 1/6 rather, you have all the 1/6, which was 10 of them, and then you have the double 6. So the number of elements of the event space there is, you can count it, that's 11. And then the probability of having this event is 11 out of obviously 36. All right. So now, what's the probability, guys, of getting no 6? Now, probability of getting no 6. Probability of getting no 6. Probability of getting no 6. I'm sure you guys admitted yesterday the use of English, that you have to be very mindful of knowing how to tackle English words when dealing with probability. So if they say probability of getting no 6, of course, that's also equivalent to saying probability of getting 0/6. That means you did not have any 6 at all. Yeah, I think I can see the correct answer right there. Because obviously, going on to check through all this is the whole places where you're going to be getting at least 1/6. Every other place apart from this is actually no 6, because apart from all here, we have every other one having not doesn't have any 6 at all. If you go on to count this, of course, you don't have to go on to count all of this. All you have to do is how many were the ones that had 6? 11. What was the total numbers? The total number of elements in the sample space? 36. So obviously 36 minus 11, that will be 25. This will give you the remainder that has no 6. So of course, the probability of having that event will be 25 over 36. This is how you tackle questions without going wrong. Now, guys, 3 dice are rolled. 3 dice now are rolled. 3 dice are rolled. What is the probability? Sorry, what is the size of the sample space? 3 dice are rolled. What is the size of the sample space? 3 dice are rolled. 3 dice now are rolled. What is the size of the sample space? Somebody said 8. Somebody said 92. Somebody said 216. 3 dice are rolled. What is the size of the sample space? Somebody said 729. Somebody said 216. Now, I told you guys yesterday, for that of dice, to get the number of elements of the sample space, the size of the sample space, it is 6 raised to the power of n. All right? 6 raised to the power of n. When we dealt with 2 dice, we said 6 raised to the power of 2. That was how we got the number of elements of the sample size or the sample space to be 36. When you're dealing with 3 dice, that will be 6 raised to the power of 3. If you do this, that will be 6 times 6 times 6, and that will give you a total of 216. All right, these are very important questions you could be asked in an objective question, and they write different options for you. So always know how to get this answer. Just so you know, guys, I'm so optimistic that you guys are going to really ace your paper, especially those of you that are really following through. I have very big faith in the fact that you guys will smash whatever is brought to you, because this is just so enlightening, and I don't see how anybody leaves here without smashing the final paper. Now, this is another question. Find the probability of getting exactly 2 equal numbers. How do you do that? Find the probability of getting exactly 2 equal numbers. Find the probability of getting exactly 2 equal numbers. Find the probability of getting exactly 2 equal numbers. No. For 2 dice, rather for 2 dice. For 2 dice. For 2 dice. Do for that of 2 dice. Doing for that of 3 dice will be quite very you guys will almost faint solving a question like that. That means you have to bring out the whole 216. Of course, if you are very smart, you can bring it out without having to even bring out the whole 216. Just looking at the logic around it. Of course, that's still possible also. All right. Having the same, getting exactly 2 equal numbers. Of course, getting exactly 2 equal numbers, that means you'll be having 2, 2, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. You count the number of elements there, that will be 6. Number of elements of that event is 6. The probability, obviously, of that event will be 6 over 36. That's 1 over 6. All right, let's see how we're going to do well. You guys, at least I can see to a very great extent, you guys are really understood the basics. This is not all about probability, guys. You still have, but you are getting grounded the right way. So just ensure, and if each of the quizzes I give you, ensure you solve them. That's a way of you consolidating your knowledge. It's really important you solve questions after learning so that at least you consolidate the knowledge. But there are still more to probability. We still have mutually exclusive events, we still have independent events, we still have conditional probability, right? And all those things are also very important to know. All right. Look at this question quickly. Let's see. A card is drawn from a standard deck. A card is drawn. A card is drawn from a standard deck. Write the sample space size. What is the size of the sample space, guys? What's the sample space size, guys? Thank you. These are very important questions. So the sample space size is obviously the NS in this case is 52. All right, 52, because you really need to. This is, the reason why you see many of your questions having this statement, because you can't do anything in probability without the sample space size. So guys, find the probability of drawing a heart. Find the probability of drawing find the probability of drawing a heart. What's the probability of drawing a heart? Okay, so good. I think I can see the answers waving right here. So, probability of drawing a heart. For you to get the probability of drawing a heart, you want to go on and define what's the number of elements in the event space. So, if you, of course, since we had this introduction at the beginning of the class, the number of elements for the event of drawing a heart is obviously 13. So the probability of that event happening will be 13, which is NE over NS. And that will be 13 over 52. And this will give you 1 over what? 1 over 4. All right. Next question. What's the probability of drawing a king? What's the probability of drawing a king? So we're done with this. The next question says what's the probability of drawing a king? Probability of drawing a king. Okay, we have different answers here. We have 4 over 52 here. We have 16 over 52. We have 1 over 13. We have 4 over 13. 4 over 52, 4 over 52, 4 over 52. Okay. Okay, we have different answers, and this is why we're here. So the probability of drawing a king. The first thing you have to deal with there is what is the event space of a king? All right. And as I told you already, we have 4 different suits And one of the constituents of each of these suits is that each of these suits has, that means for hearts, we have one king there. For diamond, we have one king. For spade, we have one king. For club, we have one king, making a total of four kings in the whole standard deck of cards. So we have four different that element. That if you needed to write the event, you obviously will write that's for art, the king for diamond, the king for spade, the king for club. So the number of element there is obviously four. Now the probability of this event happening will be, of course, NE over NS. And the NE here is obviously 4. Now be 4 over 52. And this will be what? 1 over 13. Please always try to express your work as much as possible to the lowest term. All right? Always try to express as much as possible in the lowest term. Now, what's the probability of drawing a red card? Probability of drawing a red card. Probability of drawing a red card. A red card. All right. Now, the first thing again you have to look for is what's the number of elements in that event space. So we have the event space, obviously, a red card. I told you already, the event space will have all the elements of hearts and all the elements of diamond in it. And heart has 13 cards, diamond has 13 cards, making a total of 26 cards. All right. This means obviously that to find the probability of this event, you'll be having, of course, NE. You can see how I'm writing my formula before solving. All right. Make sure that you always write out your formula. Even though we know what you were trying to do, always include your formula. All right. Now, the next question: what's the probability of drawing a face card? A face card. Probability of drawing a face card. A face card. What's the probability of drawing a face card? I believe we are done with this. Probability of drawing a face card. So, of course, for you to be able to answer this question, you must know the event space. So, what are the elements of the event space of having a face card? Of course, I want you to understand that when I started this class today, I explained to you that we have different classifications uh, when dealing with cards. This standard deck of cards. Face cards are categorized as, these are the constituents of face card: Jack, Queen, and King. These are classified as face cards. All right. These are classified as face cards: Jack, Queen, and King. All right. So now, can you now go on to answer the question, probability of drawing a face card? Why am I seeing over 56 in somebody's work? Do we have 56 cards? The probability of drawing a face card, obviously, you go on to ask yourself, what is the event of the event space? Because the event space will include Jack of all that means the Jack for hearts, the Jack for hearts, the Jack of diamond, the Jack of uh, spade, and the Jack of club. Same thing goes for Queen, Queen, Queen. You have the 4 queens, and then you have the 4 kings. Now, if you go on to talk about the number of elements in this event space, you'll be having a total of 12. And the probability of this event happening, NE over NS, that will be 12 over 52. And that will give you a total of what? 3 over 13. I told you, always cut down your work so that you don't miss your marks. Always cut down your work. So what's the probability of getting a number card? What's the probability of getting a number card? Number card. Probability of getting a number card. Probability of getting a number card. So what do you get as your number card? Probability of drawing number card. Number card. So you need to first be able to highlight the total number of elements in the event space. Number cards. So obviously we have the number cards for each of the suits. All right. And we have how many number cards in one suit? I told you we have we have 2 to 10. Number cards, we have okay, so what are your answers? For art, we have number 2 to number 10. That means we have 9 different cards. All right. So we have 2 to 10 number cards. Okay. So when we have 2 to 10, I believe we started with that. So obviously, you have 9 cards that are numbered, number cards for each of the suits. So obviously, 2 to 10 for arts, 2 to 10 for diamond, 2 to 10 for spades, and 2 to 10 for clubs. That's 9 different number cards. So 9, 9, 9, 9. The total number of elements in that event space will be 36. And then the probability of that event will be 36 over 52. All right. Now, check this question out also. What's the probability of having ace, of getting, probability of getting, of picking an ace? What's the probability of picking an ace, of drawing an ace? What do we have as the answer there? So I told you we have ace for each of them. We have ace for hearts, we have ace for diamond, we have ace for spade, we have ace for club. So obviously your number of elements in that case for aces, we have 4 aces in all in the whole set of cards we have. And then the probability of dealing with, of drawing an ace will be 4 over 52. And that will be 1 over 13. So make sure the major thing you have to do is that you must always be able to recognize your sample space and your event space. A card is drawn, guys. Find the probability that it is not a heart. A card is drawn. Find the probability that it is not a heart. A card is drawn. Find the probability that it is not a heart. Find the probability that it is not a heart. The probability that it is not a heart what did you get your answer as? Probability that it is not a heart is what? People are writing 3 over 4. 3 over 4, okay. So the question is, when you look at this question, you can go in a very simple direction. You have your understanding of what cards, of the number of how your cards are being specified, the classifications of each of the different suits. We have 13 cards that are hearts. We have, of course, 52 minus 13, which is equals to what? 39. So we have 39 that are not hearts, of course. So when the question says find probability that it is not a heart, of course, you are dealing with these ones. These are the 39 of those cards are not hearts. 13 are hearts, 39 are not hearts. So the probability here, of course, your number of elements in that event space is 39. All these other elements, that means that of diamond, that of spade, that of club. All the elements of those ones are the elements of the event space for this question. All right. So we have club, spade. If I'm supposed to write out the event space, it will be obviously diamond, all the elements in diamond, all the elements in club, and all the elements in spades. All the elements that has all, because ones that these are the ones that obviously you obviously don't have hearts being included in. That art is not included in any of all these ones. And this is 13 cards. This is 13 cards. This is 13 cards. 13 times 13 times 13 will also give you 39. So any direction you want to move through, of course, you are still very fine. So the probability of not having art will obviously be what? 39 over 52. Can you break this further? You can break this further to have 3 over 4. That's great. All right. So you can see how interesting this thing is. Is it not? Quite very interesting. Now, a die is rolled. Let's run quickly to a die. A die is rolled. Just this is very simple. Find the probability of a prime number. A die is rolled. Find the probability of a prime number. A die is rolled. One die is rolled. Probability, it's a prime number. Of course, the event of a prime number, when you roll a die, what's the sample space? We have 1, 2, 6. And we have the event for prime numbers. We have 2, 3, and 5. Of course, the probability that this event happen will be n of e over n of s. N of e is obviously 3. N of s is obviously 6. That will be 3 over 6. That's 1 over 2. You can see how nice and simple these things are. A student chooses a day randomly. 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 Find the probability it is a weekend. A student chooses a day randomly. So the question is for you to find the probability that it is a weekend. You guys are very smart. I like that. A student chooses a day randomly, find the probability it is a weekend. Of course, the sample space is obviously Monday to Sunday. The event space for having a weekend is obviously Saturday and Sunday. Of course, n of e here is 2, and the n of s is what? 7. So the probability of this event of choosing a weekend is obviously going to be 2. That's n of e over 7. All right. A number is selected from 1 to 20. Find the probability it is divisible by 5. A number is selected from 1 to 20. Find the probability it is divisible by 5. A number is selected from 1 to 20. A number is selected from 1 to 20. So the question is for you to find the probability that it is divisible by 5. So what do you have to do here? Number one, you know your number of elements of your sample space is obviously 20, right? To bring out your event space, you want to go on to find numbers from 1 to 20 that are divisible by 5. We have 5, we have 10, we have 15, we have 20. These are the numbers that are divisible by 5 in this sample space. Of course, the number of elements of this event space is obviously 4. The number of elements of your sample space is obviously 20. So the probability of having this event will be, of course, the number of elements of the event space over the number of elements of the sample space. And this will be obviously 1 out of 5. A letter is picked from the word probability. A letter is picked from the word probability. A letter is picked from the word probability. Find the probability it is a vowel. To find the probability that it is a vowel. So a letter is picked from the word probability. Find the probability that it is a vowel. Now, the very first thing you want to do here is to highlight. This is your sample. This obviously is your sample space. And the number of elements of this sample space will be what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 number of elements of the sample space. Now, the vowels, the event of having vowels, of course, you have to know your vowels. We have O, we have A, we have I, we have I. Do we have any other one? Okay, looks we have O, A, I. So these are the different elements of this sample space. All right. Now, the number of elements of this event obviously is 4. So to get your probability of this event happening will be 4 out of 11. This is the bedrock and the pathway to get success in probability. You just need to be very smart. I told you already, identify your sample space, identify your event space. You can't miss any of this question. So 2 coins are tossed. 2 coins are tossed. Find the probability of number 1, same outcome. 2 coins are tossed. 2 coins are tossed. Two coins are tossed. You have to find the probability, question number 1, of same outcomes. That's the first one. Find the probability of same outcome. Two coins are tossed. So two coins are tossed. To find the probability of same outcomes. Now, I told you guys yesterday, of course, the sample space for two coins being tossed, we have HH, we have HT, we have TH, we have TT. So the first question said probability of same outcomes. The event space here will be HH and TT. This is same outcomes. This is what it is meant by getting the same outcome. Now you go on to have the number of elements of this. We have 4 here, the sample space. Then the number of elements of your event space, we have 2. Obviously, your probability of this event happening will be the number of elements of the sample of the event space over the number of elements of the sample space. And this will obviously give you 2 over 4, which will be 1 over 2. All right, question number 2. Find the probability of different outcomes. All right. Now find the probability of different outcomes. What is asking for why we can't have just I? Because we have those two highs are both they are two different outcomes. So it's probability of the same outcome of different outcomes. What's your answer? Do I have different outcomes? I'm trying to get the answer for different outcomes. Okay, 1 over 2, 1 over 2. Okay, so for you to find that for different outcomes this time around, of course, the sample space remains the same, but your event space will have to change because we're dealing with different outcomes here. For different outcomes, your event space will obviously be HT and TH. Of course, you are still having the same number of elements there as 2. So the probability of this event will obviously be 2 over 4 still, which will be 1 over 2. Now, 3 coins are tossed. 3 coins are tossed. Find the probability of at least 2 heads. 3 coins are tossed. 3 coins are tossed. 3 coins are tossed. 3 coins are tossed. Find the probability of at least 2 heads. So you have to find the probability at least 2 heads. Okay, have you answered this before? Okay, I wasn't aware of that. I thought we solved this one just on the basis of the event, because yesterday we did more of events. Okay, let's modify the question. Obviously, what's the probability of getting at most 2 heads? At most 2 heads. If you have solved at least 2 heads, at most 2 heads. What's the answer? 3/8. When you're dealing with at most 2 heads, 3/8, 7/8, you're having two different answers there. At most 2 heads, obviously, I don't have to write out all the sample space. At most 2 heads. At most, the highest must be 2 heads. If it said the highest must be 2 heads, that means you're okay with seeing 2 heads, you're okay with seeing 1 head, you're okay with seeing 0 head. Guys, can you flow with this? So obviously, your interest is in everyone that has any of all these things. At most 2 heads. At most. Now, that of 3 head is the only exemption. I'm sure you know how your sample space went. We have HHH, on and on and on. Then we have TTT. Now, this is the only invalid one in this event space. Every other one, don't forget we had 8 different elements here. So apart from this HHH, every other one will be valid. So the number of elements of that event space will be 7. So the probability of this event happening will be 7/8. You need to understand the differences between at most and at least, and understand how to always interpret the question. And one of the common mistake that many students often make is always around dealing with 0. Many people always omit 0 out of when you go on to the distribution functions. Many people always ignore 0. They always ignore the 0 side of things. It also happens under distribution. When you're dealing with Poisson distribution, binomial distribution, you're going to be doing that very soon. That's what probably in some few weeks or months you'll be dealing with binomial Poisson distribution. Most people often they are like an offset from probability, and that's why your probability plays a very key role in being able to solve those other questions. Now, for someone that asked me to come again, the question said at most 2 heads. That means the highest you must see is 2 heads. Now, 2 heads is accepted. You are very fine with seeing 2 heads. Now, you are also fine with seeing 1 head, and you are also fine with seeing 0 head because you said at most. All right. Now, if you said at least 2 head, that means the lowest you must see must be 2 heads. All right. If you see anything below 2 heads, you will not accept it. Now, when you go on to your sample space that has to do with 3 coin, you have the first one having 3 heads, you have the last one having 0 heads. For at most 2 heads, obviously, you are very fine with picking the 0 head, but you are not fine with picking the 3 head. So that's the reason why you omit the 3 head, but you include the 0 head. In that case, you'll be dealing with 7 different, only apart from the HHH, you're dealing with 7 different outcomes. All right. So solving questions like this they play a very key role in being able to ace your exams. What's the probability of getting at most 1 head? Let me ask that and see if you have gotten it. At most 1 head. Now, at most 1 head. No longer 2 heads now. At most 1 head. What's going to be your reaction to that? At most 1 head. So in this case now, they said the most, the highest should be 1 head. Okay, I'm getting different answers. I see 1/6. I see 1/2. I see 3/8. Obviously, you guys are still struggling with this. Now, look at it. We're having different answers. Now, at most 1 head. That means the highest you want to see is 1 head. In this case, in the case of at most 1 head, 1 head is the highest. 0 head is also included. All right. Now, if you go on to open up your sample space, because in this case that will be needed. If you really want to be able to answer this question, you would need to know your sample space, because getting at most 1 head means you have to pick all that had 1 head and also the one that had 0 head. Obviously, you know the one that had 0 head was TTT, but to get for the other ones, you have to go on to pick them out. So obviously, you know, for your sample space, you had HHH, we had HTT or HHT. This is excluded now. At most 1 head. You only want 1 head or 0 head. Then we have HTH, HTT, then THH, then THT, then TTH, then TTT. So when you say at most 1 head, obviously, this is included 1 head. This is included 1 head. This is excluded. No, sorry, this is excluded because this is 2 head. This is included 1 head. This is excluded. This is included. This is also included. Let me see your answers. Wow. How come you guys got that varying answer? What's really going on? Are you seeing, it looks like many of you are still struggling with this. 3/8. I'm saying 3/8. So obviously, at most, 1 head will be 4, because we had 4 elements there over 8. Guys, what will be at most 3 heads? At most 3 heads. At most 3 heads, guys. At most 3 heads. What's going to be the answer to that? At most 3 heads. At most 3 head is going to be what? Somebody wrote 1/8. Somebody wrote 7/8. Somebody wrote 1. At most 3 head. At most 3 head is something you should be able to relate well with. At most 3, that means the highest you must see is 3 head. When you toss 3 coins up, I want you to understand that if this case of at most 3 head will always come out, because it doesn't matter whatever comes out, it's still going to be categorized under at most 3 head. What does that mean? That means we're dealing with 3 heads at most. They said the highest must be 3 heads. 3 heads is permitted. 2 heads is also permitted because this is still within the at most 3 heads. 1 head is also permitted, and 0 head is also permitted. All these are outcomes that will always happen when you toss a coin up. You toss three coin up rather. So this is what we call a certain event. It's certain that you will have at most three head. So in this case now, you are having everything. That will be 8/8, and that will give you 1. Now, a little bit, let's just do a little bit run up around this at most and at least. What will be at least three head? At least three head. What's going to be the answer for at least three head? Now, at least three head. At least three heads. What's going to be the answer to that? At least three head. At least three head. What's going to be your answer to that? At least three head. Understand the language. The least you must have. At least you should have three heads. Now, if you go on to this thing, the meaning of least means the least, the lowest you must have. That means must be HHH. Going on into all this right here, I'm sure you can see that the event space that houses at least three head is only one event that occurred that has at least, the meaning of at least three head means the lowest must be three head. By the way, you cannot have anything more than just this because there is no four head. But you understand the whole thing I'm trying to bring out from what I'm doing right here. Let's try at least two head. Let me see what you're going to do. At least two head. At least two heads. What's going to be at least two heads? At least two heads. What's it going to be? At least two heads. The least you should have now is two heads. What's going to be your answer to that? At least two heads. When you say at least two heads, that means you're dealing with the least must be two heads. Two heads is permitted because they said the least must be two heads. Then also three heads. That's two heads or three heads. They are both permitted. All right. Now, if you check through on all this, two heads, three heads. We have three heads here. This is okay. We have two heads here. We have two heads here. We have two heads here. That's how. What was you guys' answer? Okay, somebody said 3/8. Somebody said 1/2. Somebody said 3/8. Now, I'm not pleased that you guys are still getting different answers. I would have loved we are all having the same answer because at this point, I'm expecting you should be very great at this. So the event space for at least three heads, sorry, at least two heads and three heads is what I've highlighted here. HHH, HHT, HTH, and THH. So this is obviously the number of elements here is obviously 4. And then your probability of that will obviously be 4 out of 8, which is 1/2. Right? So that's the way it works. Now, can you do for at least one head? At least one head. Now, at least one head. At least now one head. The least you must have is at least one head. I would love to see that we are all on the same page. Because after this class now, you are done with everything around all this. The next one will be a different level. So at least, yeah, I love that I'm seeing the same answer. Obviously, I'm hoping it's not a wrong answer. So at least one head. That means the least you must have is one head. One head is permitted. Least must be one head. Two head is obviously also permitted. And three head is obviously permitted. The only thing not permitted here is zero head. The only thing not permitted is zero head. Because this is the least. The meaning of at least means this is the benchmark. The least must be one head. So only TTT is excluded because apart from TTT, every other one has at least one head inside it. And obviously that gives me a total of 7/8. Now the last question here, at least zero heads. At least zero heads. At least zero heads. At least zero heads. What's it going to be? At least zero heads. at least 0 heads. That means the least you must have is 0 head. So in this case, 0 head is permitted. Okay. Some people wrote 1/8. Some people wrote 1. How do you get the varying answer? At least 0 head. In this case now, everyone here has at least 0 head because TTT is 0 head. Every other one is also at least 0 head. Here we have 1 head. Here we have 0 head. Here we have 1 head. Here we have 1 head. Here we have 2 head. Everyone has at least 0 head, right? So this obviously gives you a total of 8. Your number of elements in the event space is obviously 8, and the probability there for that event will be 8/8. This will obviously be 1. So guys, your timekeeper is already showing the time. It looks like we have a timekeeper right here. And guys, I want to really tell you guys that you cannot go wrong with all this. With all this, I can assure you 100%. You guys are doing really great, and this sacrifice cannot be in vain. You see, tomorrow we're moving to the next level on this. We'll be talking about combination of events, mutually exclusive event, independent event, and wherever the time can afford us. We also have conditional probability to still talk about. So step by step, by God's grace, by 9 a.m., you'll be having your quiz again. Guys, make sure you all participate. All right, make sure you have participated. Make sure you have participated in the past one, and make sure you participate in the one coming up. All right. So, guys, it's been a very pleasing pleasure to mentor you guys in mathematics. I really hope for the best for you, and I believe it will not be in vain. Thank you so much for joining. Someone is asking about I've eaten. Yes, I've eaten. Thank you for your concern. Thank you for everything. Thank you. Thank you also. Hilarious people you started. Okay, it will not be in vain. It will be in your heart, Riba. Okay. All right, guys, enjoy yourself. Someone is asking, what did I eat? Do you want to give me food? I should share my food with you. Someone is asking if I'm supporting Iran or USA. I'm supporting mathematics. I'm supporting Nigeria. Actually, who be this one with the right alphabet? Jimmy. Jimmy don't dey press something where you don't know. Can you see? Guys, good night. It's been a very great time. Good night. Good night.